Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Atom to Molecule from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. First, the atomic potential for the hydrogen atom is being explained by Schrödinger equation in polar coordinates. Second, the radial wave function and the corresponding radial probability density functions are discussed. Third, the molecular orbitals, which are formed from the combination of atomic orbitals like bonding and antibonding orbitals, are discussed. Lastly, the schematic representation of pi and sigma bonds. So let us start with a basic introduction about the module. To study the different properties of carbon-based nanostructure, one has to start from the carbon atom, then the molecule, and then to the solid. Quantum mechanically, each atom is represented by a set of atomic orbital, a mathematical function obtained by solving the Schrödinger equation of the atom. However, except the hydrogen atom, exact solution is not possible. Determining the energies and wave function of many electrons in an atom or in a solid is truly a many-body problem. Nevertheless, there is much to be learned from the exact solution of hydrogen atom. So under the appropriate approximation, many electron atoms and many atomic molecules can be built from the hydrogenic atomic orbital. Applications of the Schrödinger equation to the hydrogen atom. Hydrogen is the simplest element. So students, one requires the accurate calculations of the electronic structure. So there is an electron and a positively charged nucleus comprised of a single proton. Hydrogen atom can be treated as a particle in a quantum well defined by the following electrostatic potential, that is VR equal to minus E square by 4 pi epsilon naught R, and it is schematically shown in this figure, which is nothing but showing the potential well due to electrostatic attraction between the positively charged nucleus and the electron. Energy levels due to confinement of electrons are also shown in this figure. So now, if we represent or rewrite the three-dimensional time-independent Schrödinger equation for this system, it can be written as minus h cut square by 2m multiplied by 1 by psi xyz, the whole multiplied by del square psi as a function of x, y, z divided by del x square plus del square psi xyz by del y square plus del square psi xyz by del z square equal to e minus v as a function of r. Continuing our discussion on the application of Schrödinger equation. So the potential, that is Vr, depends on the distance r between the proton and an electron. So we have to transform to the spherical polar coordinates because of the radial symmetry. And the transformation is as follows, that is x is equal to r sine theta cos phi, where r, theta and phi, they have been represented in this figure. That is x, y, z coordinate system has been transformed to r, theta and phi. So x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. So we can write r is equal to the root of x square plus y square plus z square, and theta is equal to cos inverse of z by r, that is the polar angle, and phi is equal to tan inverse of y by x. So theta is the polar angle and phi is the azimuthal angle. So if we transform the Schrödinger equation into the radial coordinate system or to the spherical polar coordinates, then the Schrödinger equation can be written as 1 by r square del by del r of r square del psi by del r plus 1 by r square sine theta del by del theta of sine theta del psi by del theta plus 1 by r square sine square theta del square psi by del phi square plus 2 mu by h cut square of e minus v multiplied by psi. So here psi r theta phi can be written as the product of r as a function of r, that is this capital R is the radial wave function, f as a function of theta, which is nothing but the angular wave function, and g of phi is the azimuthal wave function. So now the corresponding Schrödinger equation for the above system, we can write it like this: minus h cut square by 2 mu del square minus e square by 4 pi epsilon naught r, the whole multiplied by psi r theta phi is equal to e multiplied by psi r theta phi. So we can expand this equation in spherical coordinate system, and it is given by minus h cut square by 2 mu square bracket 1 by r square del by del r of r square del psi by del r plus 1 by r square sine theta del by del theta of sine theta del psi by del theta plus 1 by r square sine square theta del square psi by del phi square bracket close minus ze square by 4 pi epsilon naught r psi is equal to e psi. So the solution of above equation can be written as psi n lm r theta phi equal to square root of 2 by n a naught the whole cube multiplied by n minus L minus 1 factorial in the numerator divided by 2n multiplied by n plus L factorial. So this whole multiplied by e to the power minus rho by 2 multiplied by rho L multiplied by Lagrangian function, that is L n minus L minus 1, and the upper side of this is 2L plus 1 as a function of rho, YML as a function of theta and phi, where rho is equal to 2R by N A naught and L 2L plus 1 N minus L minus 1 as a function of rho is the generalized Laguerre polynomial of the order of n minus L minus 1, and YML as a function of theta and phi is the spherical harmonic function of degree 1 and order m. So, three principal quantum numbers, that is n, that is the principal quantum number, orbital angular momentum quantum number, small l, and magnetic quantum number m, takes the values as n is equal to 1, 2, 3, etc. So then small l is equal to 0, 1, 2, 3 till n minus 1, and m is equal to minus L to L. So the corresponding energy eigenvalues, including the fine structure correction, are given by ENL plus minus half is equal to minus MEC square, the whole multiplied by 1 minus small bracket 1 plus square bracket of alpha by n minus L plus minus half plus square root of square bracket L plus minus half plus half to the power of 2 minus alpha square bracket close to the power 2. Now this small bracket close, and this is to the power of minus half, where alpha is the fine structure constant and small l plus minus half is the total angular momentum quantum number, where plus minus half stands for spin up and spin down. Probability distribution functions. We must use wave functions to calculate the probability distributions of the electrons. Next, the position of the electrons is spread over the space and is not well defined. Then we may use the radial wave function, that is capital R as a function of r, the small r, to calculate the radial probability distributions of the electron. The probability of finding the electron in a differential volume element, that is d tau, is dp is equal to psi star as a function of r theta phi multiplied by psi as a function of r theta phi d tau. Probability distribution functions. So students, let us now discuss the probability distribution function. The differential volume element in spherical polar coordinates is given by d tau is equal to r square sine theta dr d theta d phi. Then the probability distribution function is given by PR dr is equal to r square multiplied by capital R conjugate as a function of r, capital R as a function of small r, dr multiplied by integral 0 to pi over f theta modulus the whole square sine theta d theta multiplied by integral 0 to 2 pi modulus of g phi the whole square d phi. But here we are only interested in the radial dependence. So we can write p as a function of small r dr is equal to r square multiplied by capital R as a function of r modulus the whole square dr. So the radial probability density, that is PR, is given by r square modulus capital R as a function of r the whole square, and it depends only on n and L. Probability distribution function. So the atomic orbital is basically a mathematical function that describes the wave-like behavior of an electron in an atom and can be used to calculate the probability of finding the electron of an atom in any specific region around the atom's nucleus. So the particular form of atomic orbital essentially defines the probability of finding the electron in a particular region inside the atoms. So now let us discuss the radial wave functions for the principal quantum number n is equal to 1 to r. And so these are the graphs which is showing the radial wave function and correspondingly the radial probability density for n is equal to 1 to r. Now students, let us discuss the radial probability density which is given by, that is small r square capital R square NL as a function of r. Now here, as you can see from this table, for a particular orbital we have a set of n and L quantum numbers, and correspondingly the value of the mean radius in arbitrary unit, that is r, which is nothing but n square a naught. So for the orbital 1s we have the 1-0 combination of n and L, and correspondingly r is given by 1.5. So as you can see from the graph that the radial probability density is shown by the blue one, the blue graph, which is nothing but r square multiplied by capital R square 1-0. Now next, correspondingly we have for the 2s orbital as 2-0, 2p as 2-1, and for 3s we have 3-0 combinations of n and L. Correspondingly, the probability density are shown by the graphs red, green respectively for the 2-0 and 2-1 combinations of n and L. Now here, as I have already discussed, that the mean radius, that is the r, is given by the integral d cube r multiplied by psi star nlm as a function of r multiplied by r multiplied by psi n lm as a function of r, which is equal to integral 0 to infinity dr r cube modulus of r n l as a function of r the whole square. So students, we have now a unique set of values of three quantum numbers, that is n, which is the principal quantum number, l, the orbital quantum number, orbital angular momentum quantum number, and m suffix l, which is nothing but the magnetic quantum number. And the allowed values of these three quantum numbers are, if n is equal to 1, 2, 3, 4, that is the integer, then l is equal to 0, 1, 2, 3 till n minus 1, and your ml varies from minus l to l. And the restrictions for the quantum numbers are n should be greater than 0, and your l is less than n, and the modulus of ml is less than equal to l. So now students, let us discuss the orbital angular momentum quantum number L. A certain energy level is degenerate with respect to L when the energy is independent of L. We use the letter names for the various L values. That is, if L is equal to 0, we denote it by the letter S, 1 by P, 2 by D, 3 by F, 4 by G, and 5 by H, and so on. So here the atomic states, they are referred to by their N and L. A state with N equal to 2 and L is equal to 1 is called as a 2p state. The boundary conditions, they require N should be always greater than L. So now this figure shows the three-dimensional shapes for the s orbital, which has one orbital, that is L equal to 0, M equal to 0, p orbital, L equal to 1, that is M can be equal to minus 1, 0, 1, which has three orbitals, px, py, pz, d corresponding to L equal to 2, having M equal to minus 2, minus 1, 0, 1, 2, which has 5 orbitals, that is d, z2, dx2, y2, dxy, dyz, dxz, dx square minus y square, and dz square. So the s orbital, as you can see from this figure, it has a spherical symmetry and exhibits even symmetry about the origin in every dimension. Other orbitals exhibits the odd symmetry about the origin. So now similarly, these pink graphs shows the f orbital corresponding to L equal to 3. So M varies from minus 3, minus 2, minus 1, 0, 1, 2, 3, having the 7 orbitals denoted by Fx, x square minus y square, Fy, x square minus y square, Fz, x square minus y square, Fxyz, Fz cube, Fyz square, and Fz square. So students, let us now discuss the antibonding orbital. The anti-bonding orbital represents the probability of finding the electrons between the two nuclei, which implies the nuclei repel each other, and it is given by psi sigma 1s star. So if we have two s orbitals, which is represented by these orange colored spherical shaped graphs, which are represented by psi a 1s and psi b 1s. So if they have the head-on overlap, then they can have a subtract overlap, which is shown by the upper graph, that is the pink graphs, that is the anti-bonding orbital represented by sigma s star, and if they add overlap, then it is shown by the green one, that is they two join together forming the bonding orbital sigma s. So we have the bonding orbital represented by the increasing probability of finding the electrons, and it is represented by sigma 1 psi sigma 1s, that is the nuclei, they are pulled together. Now this figure shows the electron densities in electrons per cubic atomic unit of length. So here we have the hydrogen molecule, which is separated by some distance, and here the electron density map of sigma 1s molecular orbital of H2, that is the hydrogen molecule, and here psi sigma 1s is represented as the summation of psi a 1s plus psi b 1s. So till now we have discussed the head-on overlap for the s orbitals. Now here we have these p orbitals which are having the head-on overlap, that is the overlap between the atomic orbitals. So here they can have a subtract overlap, which is shown by the upper figures, that is the pink ones, having the molecular orbitals which are the anti-bonding orbital sigma p star, and they can have the add overlap forming the bonding orbital shown by the green one represented by sigma p. Now if these p orbitals have the sideway overlap, that is the buildup of electron cloud above and below the plane on which the bonding atoms lie, that is the atomic orbitals, they have the sideway overlap, that is overlap between the atomic orbitals. So if they have the subtract overlap shown by the upper figure, that is the pink one, then it is represented by the anti-bonding orbital pi p star, and if they have the add overlap shown by this green one, that is the bonding orbital represented by pi p. So in order to determine the electronic structure of molecules, we have to consider multiple electrons and multiple nuclei. So considerable simplification can be achieved by assuming that the nuclear positions are fixed. Under Born-Oppenheimer approximation, the Schrödinger equation is then solved for electrons in a static potential. So finally, the solution is optimized by minimizing the total energy out of the different arrangements of the nuclei are chosen, and the solution is optimized. However, with all the simplification, the solution of multi-atomic molecule is extremely complex and generally solved by numerical techniques. But a good starting point is that the molecular orbital are the linear combinations of the atomic orbitals, That is, if phi is the molecular orbital and psi I is the atomic orbital, then phi is equal to summation over I equal to Ci psi I. A chemical bond is defined as a filled molecular orbital with lower energy than the constituent atomic orbital, stabilizing the molecule. So now students, let us discuss the pi and the sigma bonds. In carbon-based compounds and nanostructures, there are two types of bonds, sigma bond and pi bond. Sigma bonds are usually stronger than pi bonds, and sigma bonds, they are formed by the overlap of orbital that are pointing directly towards one another. This we have discussed earlier. And the sigma bonds are the strongest type of covalent chemical bond. Robustness of the sigma bond comes from the fact that if two atoms are connected by a sigma bond, rotating one of the atom around the bond axis doesn't break the bond as shown in this figure. On the contrary, in case of pi bond, the bond between the two atoms gets broken when one atom is rotated around the bond axis. It is also shown in this figure. The common forms of sigma bonds are S plus S, PZ plus PZ, S plus PZ, and DZ square plus DZ square. The carbon-carbon double bond composed of one sigma and one pi and has a bond energy less than twice than that of single carbon-carbon bond. This indicates that the stability added by the pi bond is less than the stability of a sigma bond. The weakness of pi bond can be explained by significantly less overlap between the component pi orbitals due to their parallel orientation, whereas sigma bonds, which forms the bonding orbitals directly between the nuclei of the bonding atoms, results from the greater overlap. So students, let us summarize what we have learned in this module. First, the solution of the Schrödinger equation is represented by the wave function psi as a function of r, theta, phi, which is expressed as the product of three functions, that is radial wave function capital R, angular wave function f, which is a function of theta, and azimuthal wave function g as a function of phi, using the separation of variable. Second, the radial wave function and probability distribution functions for various values of principal quantum numbers n and l were plotted with the radius. Third, the molecular orbital, that is sigma, by combining the atomic orbitals of s, which can be bonding and antibonding, and pi, by combining the p atomic orbitals, may be bonding and antibonding. Thank you.